Okay there, how's it going? We're doing the exercises from Modular Functions by Tom Apostle. This is chapter 1, and this is problem 1. So the first problem says, given two pairs of complex numbers, omega 1, omega 2, and omega 1 prime and omega 2 prime with non-real ratios, so I should say that these two things are not real. Okay, prove they generate the same set of periods if and only if there's a 2 by 2 matrix A, B, C, D with determinant plus or minus 1 and integer entries such that you can transform omega 1, omega 2 into omega 1 prime, omega 2 prime. So we'll start with this. There's the first direction, which says that the two lattices are the same, implies there exists this matrix. So we'll start with this one. So let's assume we are assuming that these are the same. So another way of saying that is that omega 1 prime and omega 2 prime are in this lattice, and omega 1 and omega 2 are in this lattice. Okay, so these two things are equivalent, right? I should put an and here. But this is the same as writing omega 1, omega 2 equals some n1 times omega 1 plus some n2 times omega 2, and that omega 2 is some m1 times omega 1 plus some m2 times omega 2. And this is, and let's go ahead and actually write the other one as well. This is also equivalent to saying, you know, kind of the inverse form of this, that we can write these original omegas in terms of a linear combination of omega primes. Okay, this is the same. I draw with a lot of arrows, and I apologize if that irritates you, but I like it logically. It makes a lot more sense to me. So this is the same thing as saying omega 1 prime, omega 2 prime equals omega 1, equals n1, n2, m1, m2 times omega 1, omega 2. And this is the same as saying omega 1, omega 2 equals n1 prime, n2 prime, m1 prime, m2 prime times omega 1 prime, omega 2 prime. Okay, now what I'm going to do is I'm going to talk about this matrix for a second. This matrix, it cannot be singular. It has to be able to transform this into something that would have a non-real ratio. So if we think about these as like vectors, right? Let's see what would happen if we had like a singular matrix first of all. Okay, if we did something like this, what would we get? Well, we would get 0 on the bottom, and we would get omega 1 plus omega 2. Well, first of all, that doesn't make sense. But if we had a non-zero element on the bottom, let's say 1, 1, here, we just get the same thing. We don't get anything that's linearly independent. And what that means is that the bottom line is that the result here, if this is singular, the result is not going to have a non-real ratio. So this has to have a determinant of at least, you know, some non-zero determinant. So let's call this m omega 1, omega 2. And we'll call this n omega 1 prime and omega 2 prime. the determinant of m can't be 0, and let's say, therefore, n equals m inverse, okay? Further, let's say the determinant of m was k. Then the determinant of n would be 1 over k. But all of these are integers. But det m and det n have to be integers. Why? Because all of the integers in here, all of the entries in here are integers, and therefore the determinant calculation, which is, that AD minus CB, that's a calculation that would fall inside the ring, and Z's are Z's a ring, so so that just leaves one possible, two possible values for k. It could either be plus or minus 1. And that's exactly what we needed. Okay, so the other direction looks pretty similar. Okay, so the first thing to note here is that matrices of this type, they form, the set of all these forms a group G under multiplication. Okay, this is pretty easy to see. I'm not even going to take time to prove it. It's, you can multiply any of these if they have determinant plus or minus 1. You're going to get something with determinant plus or minus 1. If they all have integer entries, they're always going to have integer entries. And there are inverses to all of these based on coprimes. And I know that because of SL2Z. But anyway, this is just important to note. This is a well-known thing, and I'm going to use it. So what is this saying? If this is true, what this is saying is this. A omega 1 plus B omega 2 equals omega 1 prime. Further, C omega 1 plus D omega 2 is omega 2 prime. This might be a little cheeky, and maybe I'll do it a little more. I'm trying to decide if I want to or not. But anyway, this is the same thing as saying that omega 1 prime and omega 2 prime are inside this lattice, which is the same thing as saying that omega 1 prime, the lattice generated by these two, is a subset of the lattice generated by these two. Now, if you buy that this is a group, the next step is really easy. All we have to do is take the inverse, take A, B, C, D inverse, and multiply it by this and this. And we actually can find this inverse. Okay. And this is just going to be, what do we do there? I think you swap, yeah, that makes sense. You swap those two and then turn these negative. Since the determinant of this is just plus or minus 1, it's either going to be plus or minus this, right? It's one of these two, I don't know. And so, what does this say? Well, these are integer entries, right? And this says that, and this is going to be equal to that. So this says that omega 1 and omega 2 are inside omega 1 prime, omega 2 prime, which says that omega 1 prime, omega 2 prime, this lattice, this lattice right here is included in this lattice. And so we have this and we have this, which means that the two lattices are the same. And that's it. Okay, so the next problem gives us a little bit of notation here. So we've got S of 0 is going to be the sum of zeros of an elliptic function in P. And S infinity is going to be the sum of the values of the poles of an elliptic function F and P. So we need to show that S infinity minus S of 0 is a period, and they give us a hint. Integrate Z times F prime over F. And maybe we'll just discuss this hint for a second. So this looks a little like that argument principle. Basically, if you have, let's say that you have an order K 0 in F of Z, and this is the full order here. There's no more copies of it in G of Z. In other words, G of Z does not have a 0 at Z sub 0. Well, if you have this, then you can go ahead and you can write the derivative of this. This is just we'll do this side first. K Z minus Z sub 0 to the K minus 1 G of Z plus Z minus Z sub 0 to the K of G prime of Z. And so if we look at the argument principle, and I'm just doing this for the zeros, the argument's the exact same for the poles. When I divide these off, what I get is I get K over a simple pole. Okay? Because I'm going to be dividing, these two are going to cancel here, and then there's going to be one copy of this on the bottom still. And then over here I get G prime of Z over G of Z. But again, G of Z doesn't have any zeros at Z sub 0, so you're not going to get anything. And when we integrate around, C, where C encloses Z sub 0, what we're going to get is, this is not going to be anything, and we're going to get K times 2 pi I. The question is, why would we integrate Z times, why would we integrate Z times F prime over F? So let's take a look at what that would give us. That would give us ZK plus Z G prime over G. Which again, if Z is 0, none of this matters anyway. So we're just thinking about Z if it's non-zero. Because it'll just multiply to be 0. But again, if this doesn't contain the 0, we're not going to get anything special here. If it's not 0, and it's not 0, like we just said. So, I mean, when I say it doesn't matter, I mean, what is the sum of, if there's five zeros at 0, the sum of those zeros is 0. So, that's what I mean when I say that. 0 plus 0 is 0. I could have said it simply, but I didn't. I'm sorry. So we don't have to worry about this. We're still just looking at this, and this is just going to give us, the residue here is just going to be whatever the value of Z sub 0 is times K times 2 pi I, right? And the same argument for poles. So what I'm actually doing here is I'm incorporating the value of the 0 instead of just looking at, instead of just counting them. So that's the reason we have this hint. Okay, so we're going to evaluate this integral. First by breaking this up into 4 parts. Okay. And so I'm going to write it like this, and well, maybe I'll get a little more space here. Let's write it like this. Okay, now what I'm integrating over is I'm integrating over Z F prime over F. So notice that, on the other one, if we're going counterclockwise here, for the argument principle, what we're comparing is C1 and C3 and C2 and C4. If I just look at these sides independently, what I'm going to be integrating over here is z f prime z over f of z. And then up here, it's going to be z plus omega 2 f prime z over z, f of z. For this one, what I'm going to be doing is I'm going to be integrating this, z f prime of z over f of z. And then over here, I'm going to be integrating z plus omega 1 f prime of z over f of z. Okay? Further, C1 is, I'm going to call this a positive orientation compared to C3, which is a negative. C2 would be positive compared to C4, which is negative. Another way to look at this is if I call this one positive, I would mean this one was negative. But I'm going to stick with this counterclockwise orientation, just kind of showing really importantly that the direction of this side is opposite the direction of this side. So here's how I'm going to write this. For C1, I'm essentially integrating this. Now for C3, I'm essentially doing the negative of C1, right, the opposite of C1, but I'm integrating z plus omega 2 f prime over f. For C2, I'm integrating z plus omega 2 f prime over f. And I'm going to call this negative 4, the opposite of C4. And then I'm integrating along C4 z f prime of z f of z. Okay? So just look at this for a second and see if we can make sense of this. So I'm really focused on these two pairs, this one and this one. And I'll use a triangle for this one and this one, right? These are the ones I'm looking at. They're in opposite directions, and you could see how, because this is elliptic, some stuff cancels. First of all of C1 cancels with this z. And all of C4 cancels with this z. And so what I'm left with is minus C1 omega 2 f prime over f minus C4 omega 2 f prime over f. This is actually the same as plus C2 So I've reduced this integral to just doing these two things. Oh, did I screw something up here? Hang on, I think I did. C2 should be, this should be omega 1. I'm sorry. That should be omega 1. And so that should be omega 1. Okay, that makes a lot more sense. What I've done is I've canceled out my sides. And so this is really dependent on the fact that this function, this is the only thing that's going to change when I go up by omega 1. And same with this. This is the only thing that's going to change when I go over by omega 1 and omega 2, respectively. So we can reduce it to this. The rest of it cancels to 0, as we've seen before. So we now look at these in terms of, if we, let's say that we wrote this out to be, let's kind of denote this here, A, B, C, and D. Okay? We're interested in the integral. I'm gonna write this one first because it has a positive sign here. From B to C of f prime over f dz minus the integral from A to B. I'm sorry, and this is going to be omega 1 times this and omega 2 times this. Okay? So we have something that looks like a period. The only thing we need to know is that these integrals here are integers. And so what I'm going to do is I'm just going to look at this one. And let's just talk about what this is. Well, if I use substitution here, I see I've got my derivative of f right here, nice and convenient. So this winds up being log f of z and then I plug in let's go ahead and write the whole thing out. This winds up being log f of c minus log f of b. Now, this function's elliptic, and I can kind of, if I'm at a pole, let's say that these are poles here, I could good Lord, what is shove? I could scoot this over just a little bit so there's no pole there and so that it's well defined. So I don't have to worry about hitting a pole. But what I know for sure is that what I'm going to get when I subtract these two is I'm going to get 0 plus some integer times 2 pi I because of the definition of log. Similarly, for this one, I get some 2 pi I times some integer, and let's call this k2, and this one we'll call k1. So what I wind up with is 2 pi I times some integer 2 minus omega 2 times 2 pi I times some integer k1. Now, if you remember in the argument principle, they actually divide off by 2 pi I. The reason they do that is because we're looking at the sum of the residues times 2 pi I. So we need to remove that if we want the number of poles, and the same is true here. So the actual value is going to be 1 over 2 pi I times the integral we just did, which is omega 1 times k2 minus omega 2 times k1, where k1 and k2 are integers, and omega 1 and omega 2 are in the lattice. So the sum of the values of the zeros minus the sum of the value of the poles is in the lattice. Okay, so number 3. There's let's see, 2 parts to this question. The first part, part A, says that we're talking about the Weierstrass P function here, that prove that P of U equals P of V if and only if U minus V or U plus V is a period of P. So let's go ahead and knock out this easy direction here. And I'll put the quotes around this. So we're saying that U minus V or U plus V is a period. So we're going to have 2 cases, and we're going to show that this implies that P of U equals P of V. Pause this whenever you get a chance. If anybody actually watches this, and try to do it yourself. Try to do these before you look at what I'm doing too, just to see if use it as a guide if you can, and maybe you'll find that I'm doing something hilariously wrong, and please tell me if I am. So I'm going to start with PU, and we'll start with the first case, and I'll call this case U plus V. So all I have to do is show that if this is a period, it works, and if this is a period, it works. That suffices. It's actually stronger than I need. So what I'm going to do is I'm going to add negative U plus V. This is going to be P of U minus V, which is P of minus V, which is P of V. Why? Because P is an even function. The second case looks like this. U minus V is a period. And so what I'm going to do is basically the same thing. I'm going to subtract U minus V, giving me U minus U plus V, which just winds up being P of V. So I have the backwards direction checked. Now I need the forwards direction. The forward direction says that P of U equals P of V implies that either U minus V or U plus V is a period. And this depends on the placement of these around the parallelogram. So what I'm going to do now is I'm going to draw the parallelogram, and we're going to get into all the different potential cases. Okay, so let's start before this by remembering some facts about P. So first of all, P is even. And this means that P of U equals P of minus U. Second of all, we know that P has a pole of order 2, which means that it has 2 zeros, or a 0 of order 2, which further means that if I subtract any constant from this function, constants are elliptic functions, that means it's got to hit every number z in the complex plane twice, 2 times. Okay? So we're going to use these bits of information to kind of deduce what would happen. We'll start with a U that's in, this is our parallelogram here, right? And I've kind of extended it a little bit so we can kind of talk about what happens. So let's start with a U here. Okay? Well, this U, first of all, is clearly equal to this over here, which is U minus omega 1. It's equal to this U down here, U minus omega 2. It's equal to this point down here. And when I say equal to, I mean after I plug it into the function, right? U minus omega 1 minus omega 2, okay? But it's also equal to minus U. Minus U. And because of that, it's equal to minus U plus omega 1. And it's equal to minus U plus omega 1 plus omega 2, right? And if we think about this for a second, we're guaranteed that these 2 points, U, if U is in the interior of this fundamental parallelogram, right, then we know that U it's somehow less than omega 2 and less than omega 1 in some sense, right? And therefore, if I take its inverse and I add omega 2 and omega 1, I wind up in the same parallelogram, okay? So the 2 points I have in that parallelogram are U and minus u plus omega 1 plus omega 2. Okay? Now you'll see that if I call these 2 points equal to each other, if I say that this is v, or let's say that I claim that p of u, and I say u is an interior, is in interior of the parallelogram P, and I say that PU equals PV, this will be our first case, then either P of U equals P of U, or hang on, let me erase this. Either U equals, and I keep screwing this up, either V equals some period translation of U, in other words, U plus N times omega 1 plus M times omega 2, or V is minus U plus N times omega 1 plus M times omega 2. And maybe I'll do primes here just to differentiate the two. So you see what I mean here? There's only two possibilities, right? It's either some period translation of this point, or it's some period translation of this point. Well, in this case, okay, and I'll call this A, and I'll call this B. In this case, U minus V equals U minus N omega 1 minus M omega 2, which is just minus N omega 1 minus M omega 2, which is clearly in the lattice, so it's a period. For the second case, we could just look at U plus V, and that gives us U minus U plus N prime omega 1 plus M prime omega 2, which gives us N prime omega 1 plus M prime omega 2, which is clearly a period. So the next thing we want to do is we want to check and see what other cases we might have, okay? So we could have something like this, where our point U is here, and then our negative point minus U is here, and then you have something similar where you have these 2 points up here. You actually have, if you include the parallelogram itself, you have 4 points on the parallelogram that are equal to each other, okay? So if it's on some edge like this, you have 4 points here. Similarly, maybe I'll switch letters here. What's a good letter? Let's say this is S. Then I'd have minus S, which would translate over here, and then up to here. And I would have 4 points on the parallelogram like this. So this would be minus S plus omega 2. And here'd be minus S plus omega 1 plus omega 2. And this would just be S plus omega 1. So I'd have 4 points to check here. But as you can see, I could just do the same thing. If U is on border of P, I could do the exact same thing. Another thing to note here is that if it's on the border of P, I could just shift P so that it's in the interior. So this second case really isn't troublesome at all. And that's enough to give us both sides of this. So that gives us the full if or only if. Okay, so the second part of this question is kind of a lot. It says let A1 to an and b1 through bm be complex numbers such that none of the differences between p if you plug in an a value and p if you plug in a b value are 0. And then you name this function f of z. And this function is just going to be a product of p of z minus p of these a values and p of z minus p of these b values. We want to prove that f is an even elliptic function with zeros at a1 through an and poles at b1 through bm. So there's a few things we have to do here. The first thing we should probably do is show that f is even. Okay? And this is as simple as proving, in other words, show f of minus z is the same as f of z. Okay? So what I'm going to do is I'm going to plug in minus z here. So I've done this. I've plugged in minus z in all of these, but the thing is that p is even. So this right here, f of minus z, is the same thing as switching these z's back, which is f of z. So good. We have that it's even. Okay, so this part's pretty easy. We also have two other things we have to verify. The first is that f is elliptic, which is doubly periodic and meromorphic. The next one is that all the a values are zeros and the b values are poles. This 3 right here is pretty easy. You could just look at the function and see that. If I plug in an a value up here, I'm going to get a 0. And I've specified that none of these quantities are zeros. So any a value I plug in down here is not going to give me a 0. Further, if I plug in a b value for z, I'm going to get a 0 down here where I'd get a pole. And again, I've specified that none of these differences are going to be 0, so I'm not going to get some funky, removable type stitch where it's 0 over 0, where maybe it's a more complicated singularity than just a pole. So 3 is pretty easy. The only thing that we really have to worry about is 2, demonstrating that this is elliptic. And so that's what we're going to focus on here. Doubly periodic. You just plug in some value, some omega equals in omega 1 plus m omega 2, and you'll see that f of z does in fact equal f of z plus omega. This should be pretty clear because these p functions are doubly periodic. So in fact, f has same periods as p. And the only thing left is that f is analytic except for the poles. And if this were a complex analysis video, maybe I would get into this further, but it's not. And what we have to realize is that the field of functions is meromorphic functions. So what I'm guaranteed is that a rational function of meromorphic functions what I'm guaranteed is that a rational function of meromorphic functions is meromorphic. And that gives us everything we need for B. I want to take just a quick second before we move on to the next one, which you'll understand why I'm doing this in a minute. There's a reason we're looking at rational functions of this, and it goes back to this idea, which I think I might have mentioned in one of the videos, that you can really make all elliptic functions out of just these two things. Okay, and this leads us to the next thing, which is prove that every even elliptic function is a rational function of p of z. Okay, so back to this. Sorry, my dog started barking. Prove that every even elliptic function is a rational function of p of z, where periods of p are a subset of f. And we're calling this elliptic function f. So again, okay, so let's just look at f, elliptic, and even, okay? And let's say that it has a set of, has poles of order 2k, 2ki at ai. Okay, where these are sets, right? Relating to each other. So this would be like A1, A2, yada 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 to AI, and corresponding orders are 2K1, 2K2, yada 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 to KI. Okay, so poles of order 2K here has to have the same number of zeros as poles. So it has zeros of order 2si at t, or sj, we'll say, at tj. Okay? What we do is we construct this sort of the same way that we've constructed all the other things, right? All we're saying is we're taking what we had last time and we're saying, okay, well, we're going to account for all the poles. We're going to say f, right? And we're going to just create the poles. So what I'm going to do is I'm going to take p of z, p of z minus p of ai, and I'm going to take that to the ki, and this will produce a pole of order 2ki at a sub I, and then I'm going to take p of z up here minus p of tj, and I'm going to take this quantity to the sj, and this will create a pole of order 2sj at tj. Okay? And, well, I should have named this in, and I should have said this corresponds to, let's say, T1 through Tm. And I'll go ahead and I'll write this out in from I1. Okay. So here I have a function that should look something like this f that I'm trying to make it look like. I guess the only question is, are there any extra poles? Do I have any extra poles? And here's kind of the nifty thing. Okay. Let's say that I have extra poles. Then I just multiply by whatever the extra poles are up here to remove them. And then I'd have extra zeros too, and I just multiply by whatever the extra zeros are down here and remove them. So we can name another rational function that takes care of the remaining poles. And we'll call this RP. And then another zero function that takes care of the remaining zeros. And what I'm left with is some rational function of p of z that has exactly the poles I want, and the zeros or whatever. Okay? Yeah. The next thing I want to ask about is what are the periods of f? And I don't have really specific information about this, except to say that if I did do something like this, if I had that p was on this lattice, right, was doubly periodic on this lattice, then I could do something like this. and I think I misspoke last time when I said they had the same periods. It's tempting to say that, but what you really find is that you don't know that. Okay? What you do know is that if you plug in a period of P of z, you get f of z back. So you do know that if you have if you have f, which is part of some other lattice, what you do know is that the lattice belonging to P at least belongs to this lattice belonging to f, in the sense that any one of these periods would work for f, but there might be more periods. You don't know. Okay, so number 5 is prove that every elliptic function can be written as some rational function of P of z plus some rational function of P of z times P of z's derivative. Now, what we need for this is a lemma. And the lemma says that every function can be written as a sum of its even parts, its even part and odd part. And here we go. We're going to write it like this for a second. So let's just, I hope I don't screw this up. What I'm going to do is I'm going to write this, okay? All right. Now, the odd part of this function is this part over here. Why is that? Because, wait, did I say that right? Hang on just a second. No, I did not say that right. So the even part of this function is this right here. Why? Because z equals minus z. So if I'm just restricting to this part, what I'm going to get is 2fz over 2, which is just f of z. The odd part is right here. Because f of z is minus f of z, is the opposite of minus f of z. So this right here is going to give me 2f of z, which is going to give me 2f of z over 2, which is f of z. So I have f odd plus f even. Now, what I've already done from number 4 is said that this f even part can be written as a rational function of P of z. Okay? What I need is to show that the odd part can be written as f prime of z times some rational function times P of z. So there's a couple of ways to do this. One approach might be to do kind of what we did before, where we just sort of paired up the poles. And that would be it would be more work, and it seems like it would be hard to explain this away. Like, why would I not use some, rational function of p prime or something like that? So I'm not going to go that way. Another idea which might be more fruitful is is looking at this as a derivative of an even function, but I don't really even have to do that. If I go back to this odd part here, okay, so if I write this f of z minus f minus z over 2, and this is f odd, then what is this? Well, what I've done is I've changed f odd a little bit to what is an even function. It's an even elliptic function. And I can represent this as some R2 of P of Z. So now all I really need is f odd is f prime of z times R2 P of z. That's all I need. And that's enough to give me this right here. Okay, so here's problem 6. F and g are two elliptic functions with the same set of periods. Okay, we're supposed to prove that there exists a polynomial p of x and y, not identically 0, that would be way too easy, such that p of f of z and g of z is some constant. Now this one threw me for a loop a little bit. I had to work on this one for a little bit longer than I care to admit. There was a stupid approach I came up with that basically just paired up the zeros. As you can kind of imagine, the reason they mention same set of periods is so that we can understand that p of z, that we're building these two functions out of, we're not going to have any issues with those periods from problem 5, right? So, without further ado, I'll show you what I came up with. I'm pretty sure this is right. If somebody knows, if anybody's watching this and can think of a better way to write this, I would love to hear what you have to say. But this is what I came up with, and I'm pretty sure this is right. So here we go. What I'm going to do is I'm going to, as in problem 5, I'm going to write out f and g as the sum of even and odd functions again. Okay. And I'm further going to write this out as the quotient. I'm going to drop my input here just so that I'm going to write this out as the quotient of polynomials in over p. Okay? So that's all I'm doing now, is I'm just writing out the quotients. All I'm saying is that R1 equals P1 of P over Q1 of P, S1 equals M1 of P over N1 of P, etc. Okay? And I'm going to start with P. I'm going to start with F. Okay? And I'm going to clear these denominators out. Okay, so I'm going to look at Q1, Q2 times F. And that's going to give me P1, Q2 plus P2, Q1, P prime. I'm then going to take P1 and Q2 and move it over to this side. And you'll notice that this equals P2 Q1 P prime. What I'm now going to do is I'm going to square this side and this side. Now this is 4pz cubed minus g2pz minus g3. Okay? So this is another polynomial, and I'll call this, what should I call this? I'll call this V. Okay? V. I'm going to do the same thing with G, and what I get there is n1 into G minus m1 into quantity squared equals m2 n1 quantity squared V. So I have this equation and I have this equation. This is in terms of F, this is in terms of G. What I'm going to do now is I'm going to take equation 1 and multiply it by m2 n1 squared. And I'm going to take equation 2 and multiply it by p2 q1 squared. Okay? And then I'm going to take the results and subtract. Okay, so and actually the way that I'm going to subtract is I'm going to subtract the first one. I'm going to subtract the second one from the first one. Okay, and here's what I'm going to get. So now I have Q1 Q2 F minus P1 Q2 quantity squared times m2 n1 quantity squared minus n1 n2 G minus m1 n2 quantity squared. Okay. P2 Q1 squared equals 0. Okay, now here's where you have to kind of bear with me a second. This is a polynomial of P. This is a polynomial of P. Okay? What I can find is a resultant polynomial of F and G such that I get rid of P here. Okay? I've already eliminated V, so I don't have P prime anymore. And so now basically what I'm doing is I'm just looking at this, and I'm finding the resultant. Finding the resultant of this monstrosity. This resultant is going to be this will be a polynomial f of f and g that equals 0. Again, if anybody can think of a better way to do this, I would absolutely love to hear it. One thought I had, I'll pause this and I'll show you where I was headed, but you'll see why I don't like this approach. So the approach I decided to give up on, was much simpler. I just don't have a lot of analytical faith in it at all. So F, I decided to just say simply, let's just give us a really simple example. okay, where these are the poles of f, and their orders. And then G, similarly, B1, B2, with S1 and S2. Okay, so these are poles and orders. Okay? If you write F, and you multiply F by G of Z minus G of A1 to the S2, K2, K1, and then you multiply that by G of Z minus G of A2 to the K2, K1, S1, and then you subtract G of Z to the what did I do here? I think this is where I went with it. 2K1, K2, S1, S2. And the thought here was, okay, so I'm killing off all the poles in F. Okay, killed off. Okay. I overkilled them, in fact, because I generated I generated way more than enough zeros to cover up these poles. But now my problem is I have S2, K2, K1, B1 poles, which are each of order S1. And I have S2, K2, K1, S2 poles, B2. Well, actually, no, this doesn't work. See, this is what I mean. I don't like this approach at all. This approach will not work, I don't think, because you have to pair up these exponents in a way that. Anyway, yeah, if you could think of another way to do that outside of really breaking. I mean, I think there's probably an easier way if you just think about the fact that P and P prime make a field of functions. Field of elliptic functions, and then something about rational polynomials. I'm sorry, about polynomials being generated by rational functions, or something. Polynomials of rational functions. There might be something clever there, but anyway, I apologize. I don't have a really nice, neat answer for this aside from what I did earlier, which I do believe is correct, but it certainly didn't make me happy.